Hello everyone. In this video, we are going to discuss the applications of Gauss's theorem. A number of applications are there, but according to our syllabus, we have only 3 applications. The first one is the electric field due to an infinitely long charged wire. So we have a thin wire and its length, it's infinitely long and it is uniformly charged. Now it's a charged wire, there will be an electric field around it. So you are going to find out the value of this electric field with the help of Gauss's theorem. So we have a very long wire. So I'm going to draw it, look at the board. It's actually very long wire, infinitely long. So infinitely long. And it is uniformly charged. So let it be positive charge. So it's completely charged, but see here, we are going to consider only a small portion of this wire. Okay, so and it will be the same for the entire wire. Okay, so now look at the board. Here it is positive charge, positively charged, and it has a charge density. The charge density is lambda, linear charge density. You know what is lambda? It is the charge per length. So the lambda is given. There is electric field around this charged wire. It's a positively charged wire. We know positive charge. The electric field lines, they start from the charge and directed towards infinity. So it will be like this. It starts from the charge and it going to infinity like this. Infinity. In all the directions there will be electric field. Not only on LHS and RHS. On either side. Not only on either side. It's in 3-dimensional. There will be a lot of field in all the direction. Around the charged wire there will be electric field. Okay, now we are going to find out the electric field at a particular point. So look at this. Let's consider a point here. Let it be point P. It is at a distance r from the wire, a perpendicular distance from the wire. It's R and that point is P, and we know the direction of electric field will be, it will be starting from the charge and it will be directed towards infinity. Okay, so this is what you are going to calculate. Now, in order to apply Gauss's theorem, we know we need a closed surface and we call it is Gaussian surface. So here we have no closed surface. So we have to imagine a surface and we consider it's a Gaussian surface. So we can consider any shape, any type of Gaussian surface, but let us consider a cylindrical Gaussian surface which is more convenient here. A cuboid also you can consider, but let us consider right now a cylindrical Gaussian surface, and the cylindrical Gaussian surface will completely enclose this much portion of this wire, not the entire wire, only this much. We are concentrating only this much. So I am going to draw this Gaussian surface here. Look at the board. This is the Gaussian surface, and also I am just making a slight change in our point P. This is point P. Okay, it's at a distance R. Okay, and the electric field is this. Now see this. The wire is the axis along the axial line of this Gaussian surface. Yes. And the radius of the Gaussian surface, cylindrical Gaussian surface is R, and that point P is a part of this Gaussian surface. Okay, clear? And the length of the Gaussian surface is also given. The length of the Gaussian surface is this one, and length of the Gaussian surface and the length of the wire which we consider both are the same, it is L, small letter L. Now we are going to calculate the electric flux passing through this closed surface. Okay, we have studied electric flux formula. Flux phi is equal to E dot A, or is equal to, it is EA cos theta. So this is the formula of flux. So in a cylindrical closed surface, how many surfaces are there? The first one, there is a curved surface. Clear? So this is the curved surface. And on the top and also on the bottom, there are two circular surfaces also there. So we are going to calculate the flux of all the three surfaces separately, and we will add all the three, and that will give you the net flux, the total flux through the Gaussian surface. Okay. Let us consider a small area. So I'm not going to consider the curved surface as a whole in the beginning. So I'm going to consider, look at this, a small area. This is a plane surface here. Okay. And this area I'm going to mark it as dA1. First one, dA1. See, it's area vector, so it has a direction. It's dA1. Okay, and what will be the direction of area vector? We have studied, it is along the normal. It will be normal to the surface. So it is the surface dA1, and this will be the normal. Clear? So the normal will be this. So this is the normal. I am marking it as n cap. N cap, A cap, or anything. So n cap I am going to write. Now see, what will be the flux passing through the small area? So the small area, not the entire one, the small area dA1, that will be E dot dA1. That will be the flux through only this small area. Okay, and how will you find out then the entire flux? That entire flux you have to integrate. So you have to integrate. So you are integrating a closed surface. So close the surface integral. So we denote it like this, the closed surface integral E dot dA1, which will give you the flux passing through the entire curved surface only, curved surface. Now let's go to the upper circular surface. So here I'm going to consider again a small area. Now the same area, but see here, this is, I am marking it's dA2. It's a vector. Second one, dA2. Now it's facing the upper side. So what will be the direction? That will be the normal. So that normal is this. So it's n cap. Now the direction of electric field. It starts from the wire and it is directed towards the infinity. So electric field will be like this. So electric field will be like this. So this is the direction of electric field. Anyway, what will be the flux over here? It will be electric field will be same, but it is dA2. So this will give you the flux through the small surface dA2. If you integrate it, if you are integrating this, you will get the total flux through the upper circular surface. Similarly, let's go to the bottom. Here we are considering another area, and it is, let me mark it as, it is dA3. It's also a vector and it is facing downward. So what will be the direction of this vector, area vector? It will be facing downward. So this is n cap, the direction of area vector. An electric field, it starts from the charge, it starts from the wire and directed to infinity. So it will be like this. So this is E. And what will be the flux through this small area dA3? So that is E dot dA3. And if you integrate, you will get the net flux through the bottom circular surface. Now, what will be the net flux through the complete closed surface? So the net flux phi is equal to the sum of all these 3. It will give you the net flux through the Gaussian surface. Now, the net flux phi is equal to line integral, surface integral, rho surface integral, it is E dot dA1. So I can write down it is E dA1 cos theta 1 plus second one, what it is? It is surface integral E dA2 cos theta 2 plus, and the third one, it is surface integral E dA3 cos theta 3. Got it? Okay. Now again look at the surface. Theta 1. What is theta 1? Theta 1 means it's the angle between electric field and dA1 in the first surface. So this is the first surface. So what is the value? So n cap and E, it's along the same direction. So it's clear that the value of theta 1 is 0 degree. Theta 1 is 0 degree. Okay. Now go to the second one. Look at the second one. Electric field is perpendicular to the wire and it's directed to the infinity, but the upper surface n cap is upward. So it's like this it is. So electric field and the the n cap. So what is the angle between them? Perpendicular. So what is the angle here? It is theta 2. So theta 2 is equal to 90 degree. Again in the same way, let's go look at this one. Same way, electric field towards infinity and n cap downward. That means electric field is in that direction and then n cap is downward. So what is happening here? Again 90 degree. So here theta 3 is also 90 degree. Now we know what is cos theta 1. Cos theta, substitute the value here. So that is the net flux phi is equal to, it is integral E dA1. Now cos theta 1. Cos theta 1 is cos 0. Cos 0 is 1. So cos 0 into 1 plus. Now again this one. Integral E dA2 cos theta 2. Cos theta 2. What is theta 2? 90 degree. Cos 90 is 0. So the second term will become 0. And again plus. And the third term, it is integral dA3 cos theta 3. What is theta 3? Again, theta 3 is 90 degree. So cos 90, again 0. So it will also become 0. So finally, you will get the flux phi is equal to, okay, your electric field is uniform at this point. So you can see the curved surface. It is at uniform distance, equidistance from the center of from the axis or from the wire. So that distance is r. So electric field at equidistance is the same. So electric field is constant, so you cannot integrate this, and now you are integrating what? Only dA1 and plus 0 plus 0. And when you integrate, you will get the total flux. Now we are integrating flux phi is equal to E surface integral dA1. When you integrate this dA1, you will get the total surface area of the curved surface. So curved surface of a cylinder, total surface area is 2 pi r into height. So here the height, I have raised the diagram. You check the diagram, you will understand on the side it's written the height is L. So you can write down that is equal to, it is, okay, I'm writing here itself. So E into, when you integrate, you will get it is 2 pi r L, equation number 1. Okay, so this will give you the net flux through this cylindrical closed surface. But remember, the flux is only through the curved surface. The upper and the bottom become 0. You know why? Because the angle between area vector and the electric field, they are perpendicular to each other. Okay. Now according to Gauss's theorem, by Gauss's theorem, We know the flux passing through the Gaussian surface phi is equal to 1 by epsilon naught times charge enclosed by the Gaussian surface. So that is q by epsilon naught. Okay, and it was given in the beginning the the line charge density of the wire. The line charge density of the wire, it was lambda is equal to q by L. So we consider small length only. You can see the diagram, you can see a small piece of wire, not the entire wire. Okay, so here that length is L and the charge of that particular wire is Q. So linear charge density or line charge density lambda is equal to Q by L, or you can write down Q is equal to lambda L. Let's substitute the value of Q here. So when you substitute here, you will get flux phi is equal to, it is lambda L divided by epsilon naught, equation number 2. Now look at equation number 1 and 2. LHS flux phi is equal to phi is equal to. So you can equate, LHS are the same, so you can equate the RHS. So from 1 and 2, so from equation number 1 and 2, you can write down RHS of 1 is equal to RHS of 2, that is E into 2 pi RL is equal to, here it is, lambda L divided by epsilon naught. So here L and L you can cancel, and finally you can rearrange this E is equal to, because you are calculating electric field E is equal to, so this will become lambda divided by 2 pi epsilon naught R. So this is the the electric field at point P. Electric field due to a line charge, due to a infinitely long wire, that electric field will be given by this equation. Okay, so you can modify this equation, you can modify this. So because see here what I am going to do, you're going to multiply 2 by 2 in the RHS. So RHS we know it's lambda divided by 2 pi epsilon naught R into 2 by 2. So when you do this one, this equation will become, see here, E is equal to, see here it's I'm writing it's 2 into 2, it's 4 pi epsilon naught, 4 pi epsilon naught, and it is 2 lambda by R. So I hope you understand why you are multiplying by 2 by 2. So we can make this into a new format, that E is equal to 1 by 4 pi epsilon naught 2 lambda by R. Why do we consider it's nothing but this is a familiar, this value we know, it's K. So I just want to convert this equation into one of our familiar format, that is E is equal to K 2 lambda divided by R, where the value of K, what is K, where K is equal to 1 by 4 pi epsilon naught. Do you remember the value of K? When you solve this one, you will get it is 9 into 10 raised to 9. Okay, so these two are the equations. So this is these two equations. Both these equations will give you the electric field due to an infinitely long charged wire. In the end, let us see the relationship between electric field and the distance. Electric field and the distance due to this infinitely long wire. Look at this, we have this equation right now, E is equal to K 2 lambda by R. Now see here, E and R. K is a constant, 2 is also a constant, lambda of the wire, that is also a constant. So what is the relation between E and R? You can write it as, that is, E is inversely proportional to R. Inversely proportional to R. That means if you are plotting a graph while taking electric field along the y-axis and this R along the x-axis, so the graph will be this. It means electric field and the distance is inversely proportional. That means when the distance increases, the strength, the electric field intensity is gradually decreasing. Okay.